well, welcome everybody to another STEM Wednesday. Today we are going to be looking at just some different ways we can use the lab disk in a physical science setting. Later throughout the month and next month, we'll also look at some other areas of science. We had Evan just a couple weeks ago do life science, so we'll have an environmental science happening in just a few weeks from now. So this is going to be really focused just on ways that we can quickly use the lab disk. It might be a student experiment. It could also just be something that you do right at the front of the classroom as a demonstration of a simple concept. And as the title states, we're going to go through 3 different physical science labs or experiments in the next 20 minutes here. And what I'd like to start out with is going to be a demonstration of frequency. And for this, we're going to be looking at using the lab disk in sort of a creative way to measure the frequency of a pendulum. So if we've never heard of a pendulum before, it's really any object that swings back and forth. Think of like a grandfather clock, for example. That would be a good example of a pendulum. And we're going to use the lab disk to actually gather some data from a swinging pendulum and then convert that gathered data into frequency. And we can even use this to look at different relationships with frequency and a pendulum. For example, looking at how frequency changes with the length of a pendulum. So if we make the string longer or shorter, and then also how that frequency changes, maybe if we were to change the mass on the end of the pendulum and see if there's any relationship that happens there as well. So I'm going to switch my camera view over here so you can see my setup. And just to quickly explain my setup here, I have a couple different things set up, so we'll get to the other ones in a second. What I have here is I have my lab disk. I have it actually laying face down. And what I'm going to be using in this lab or this experiment is the distance sensor. So on the back of the lab disk, I'm using the distance sensor. So if you have a lab disk, this can be done with either the Labdisc GenSci, with the Physio, or with the Labdisc Xploris, because all 3 of these lab disks have that distance sensor available on the back of them. Switch over so I can show you how I'm actually going to be collecting that data. Yeah, so again, here's that lab setup, just so you see it here. And I've got that lab disk facing upwards, so the distance sensor is facing at my pendulum. You can just see the ball. I can't get all of it in the screen at one time here, but I just have a ball tied onto a string so I can swing that ball back and forth. I chose a ball that's large enough that it's able to be picked up by the distance sensor of the lab disk. If I used too small of a ball, it's very possible that the sensor is not going to see that ball passing through sort of its window of view. And we won't see anything happen. So I'm going to share GlobuLab. So GlobuLab is where I'm actually going to be able to visualize the data here. And like I said, we're using that distance sensor to visualize or to actually record data that's going to lead us to finding the frequency of the lab or the pendulum. And so like you see here, I have my distance sensor selected, and I'm going to take and use a high sample rate. So I see lots of data points that are going to come in here. And when I'm ready, I'm going to run this. I will pull back on my pendulum and let it go and swing back and forth in front of my distance sensor. And really, that's all I need. So now from here, I'm able to actually look and see everywhere where there's one of these little blips in my line. So all this garbage at the beginning is when I had my hand over the distance sensor pulling the pendulum back. But I can look at every single one of these little deflections in that straight line. And those are indicating the points where the ball is passing back and forth over the distance sensor. Then what I'm able to do is I can actually take and place some markers directly on those points. Notice when I place a marker, it gives me the time at that specific point. And I'm going to place a marker here, and I'm going to skip one of these. And the reason why I'm skipping one of them is because if I think of how the oscillation happens, it passes through the midpoint twice during one full oscillation. So I place that second marker there. And then I have my two times. I have the time it first passed through, 3.47 seconds. And then I have 4.59 seconds, or 59 seconds the second time it passes through. If I find the difference between these times and then take and divide 1 by that difference, it will actually give me the frequency of that pendulum in units of hertz. So basically using this equation that I have on my PowerPoint slide here, we would divide the total number of oscillations by the time it takes those total oscillations to complete. So in that case, I looked at one oscillation, so I divide 1 by the time for one oscillation to complete. So this can be expanded to multiple different areas of physical science. High school classrooms, we could use that distance sensor, high school and middle school classrooms, we could use that distance sensor in a similar manner with an object oscillating on a spring above the distance sensor. And then we can measure the frequency of oscillations, and we can look at something called Hooke's law, which deals with spring deflection based on mass and strength of the spring. At the elementary school level, we can look at just frequency, and we can relate frequency to pitch. When we think about frequency, we often think of sound and how we hear different frequencies. And we can relate this frequency to the pitch, maybe, and think of like a guitar string vibrating. And students can think about how changing the length of a guitar string changes pitch. We can relate that back to this pendulum vibrating back and forth. Now, my second experiment, we want to talk about bungee jumping and look at how we can measure acceleration using the Labdisc and how we can think about how G-forces act on our body. If you've never heard of G-force before, G-force is the force that you experience when you accelerate. So you might feel this when you're going around a turn in your car super fast. It's that force that sort of makes you feel like you're getting pushed to the other side of your car when you're turning. If you've ever been skydiving before, if you ever jumped a good distance, it's that feeling, it's that force that you feel when you get that like stomach rising up into your chest feeling. And we can actually measure this force with the Labdisc. So my setup here is going to be a little bit different. I am going to pan over my camera here to where I have actually my Labdisc suspended from a rubber band, and I have it strapped to my wall. So my Labdisc can sort of oscillate up and down on that rubber band strapped to the wall, and I'll stop sharing here just so we can see that a little bit better. If I wanted to do a little bit of math with this and can do some comparisons between acceleration and height, then I'm letting the Labdisc fall, or maybe acceleration and rubber band strength. I've also taped behind that a meter stick. You can't probably in the video see the actual numbers on the meter stick, but I have tape behind there a meter stick so I can take and drop that Labdisc from different heights and measure that change in acceleration based on that change in height. And yeah, I see a question in the chat. Is the rubber band attached to the gray part of the Physio Labdisc? Yes. So I have the rubber band looped through the colored part of the Labdisc. There's a basically spot where you can loop it through there to hold on. There's also on the bottom of the Labdisc, there's a little tab that you could also hook it into. So there's multiple spots that you can move it or hook it into. But yeah, it's currently hooked into the spinning part of the Labdisc, if you want to call it that. Let me get this connected here, and we'll show this one. Apologize for that. My computer is completely freezing up and not allowing me to connect to that Labdisc. So instead of connecting to it and showing the experiment, show you what I would do, and then I'll show you what the data would look like after I've connected it. So all I would do here is I would lift my lab disk up and allow it to drop and oscillate back and forth. And it doesn't matter if it's hitting the wall at all, because what we're going to get is we're going to just look at one axis of acceleration. And the way that I have my lab disk hung, and the way you probably will hang your lab disk as well, you want to look at the x acceleration. When you record acceleration with the lab disk, you'll actually see that it records acceleration in the x, y, and z direction. And what we'll see here is on my graph, and I'll share my screen here again so you can see what this data might look like. This is the data you would expect to see from this lab disk oscillating up and down. At rest, it should be sitting around 1G. And the reason for that is we all experience 1 times the force of gravity at all times. G-force is multiples of that. So at its highest point on that very, very first drop, it actually reaches down to negative, what is that, 0.7 Gs, and then up to positive about 1.5 Gs. That means 1.5 times the force of gravity. So to put that in perspective, if that was you hanging on that rubber band instead of the lab disk, when you hit that lowest point and started getting snapped back up to the top, it would feel to your body, you would feel like you're about 1.5 times your normal weight. And the more G-force you experience, the heavier you would feel as a person. So fighter pilots, for example, feel 8 to 9 Gs. So they feel almost 8 to 9 times as much as they typically would weigh standing on the surface of Earth. I do see a question, how do I have the rubber band attached at the top? It wasn't attached to the tape of the meter stick. I have it tied on to a little child safety thing for my son to keep him out of my closet of goodies. Let me see if I can pan up here so you can see it. It's like a clear plastic thing that keeps my closet door from being opened. And it has a little hook on the end of it so I could hang it right off of that. If you don't have a way to hang it off the wall like that, you could also, yeah, like basically like a towel hanger or something like that. So you could use a towel hanger or wreath hanger. If you have a lab stand in your classroom that's tall enough, you could use something like that. Even like a tripod might even work. But if you don't have any of those, one person could even stand and hold the rubber band against the wall, while a second person actually allowed it to oscillate up and down. And we're going to move to our third and final experiment example here. And this one is going to be on the ideal gas laws. The ideal gas laws deal with the relationship between pressure, volume, and temperature of a gas. And there's a bunch of different ways that we can test these relationships. So the 3 different things or ways we can test and visualize this relationship is we can look at the relationship between temperature and pressure, relationship between temperature and volume of a gas, and relationship between pressure and volume of a gas. But for this setup, again, I'm going to be using a GenSci lab disk in this case. But this one you can use the environmental science one as well. That has that temperature. Actually, you can use any of the lab disks, environmental, physio, or biochem in it, and even the Xploris, if you're doing the temperature measurements. Pressure, you are limited to just the physio and the GenSci lab disks if you're doing any relationships with pressure. So I'm going to show a couple different setups here. The first one here, I'm going to be using a syringe. And I'm going to take my lab disk. And let me stop sharing so you can see my setup here. The first is going to be a measure of, or a test of the relationship between pressure and volume. So on the side of my lab disk, I have a pressure sensor. It looks like on the button, it looks like there's a couple squiggly arrows on there. There's a little metal port. And on that port, the first thing I'm going to do is I'm actually going to screw onto that port a syringe. And I'm going to start with the syringe opened all the way. And this one, I'm actually not going to graph any data. This one I could actually just do directly off the lab disk itself. And so I'll bring this up a little bit closer here. And what I would do is if I was doing this with students, I would have students actually recording this data as we change the volume of air within the syringe. So right now I'm starting with that syringe at 10 milliliters of air. And we see my pressure is reading about 102 kilopascals. Right, then what I would do to demonstrate this relationship, I would move the syringe in 1 milliliter at a time. Start at 115, and see the pressure increase. I decrease my volume again, excuse me, and see my pressure increase, decrease the volume again, I see pressure increasing, decrease the volume again, I see pressure increasing. So I can repeat this multiple times. I can take those multiple measurements. And if I plot pressure as a function of volume, so pressure on the y-axis, volume on the x-axis, I actually see that I get a nice relationship, and I show a nice relationship between those two values. And I see a question in the chat about a specific type of syringe for the experiment. So if I'm trying to connect a syringe directly to the lab disk, if you have a lab disk that's capable of measuring pressure, a small tube will be included in the box. The tube will look like this one here that I have connected to my second part of this experiment. But if you want to connect a syringe directly to the lab disk itself, the type of syringe you're looking for, it's called a Luer lock, L-U-E-R, lock, L-O-C-K. I mean, it's just the type of thread that the syringe has on the end of it. So it has to be able to thread and twist onto that port there. If you look at a syringe, if the syringe has threads, it's going to be the correct one. You just don't want a syringe that has a needle attached to it. That's not the type of syringe we're using here. Okay, now I'm going to go in here and set up for my second experiment. My second experiment, dealing with the ideal gas laws, I'm going to look at the relationship between temperature and pressure. So what I'm doing now is I'm connecting a temperature probe to my lab disk, and I'm going to lower this temperature probe down into my little beaker of hot water here. If you didn't have the ability to do this with hot water, or you're worried about students burning themselves, you could do this exact same experiment using ice water instead. And then on the other end, what I have here is I have that tubing that came with my lab disk connected to a little Erlenmeyer flask. I put a stopper in it, and I've connected that tubing in there. So I have a set volume of air trapped within that flask. And I'm going to connect the other end of that tubing to my lab disk pressure sensor. And now I'm going to go share on GlobiLab. I'm going to set this up. So in GlobiLab here, I've got that lab disk connected again. Rather than measuring distance, I'm going to be measuring air pressure. And I'm also going to measure external temperature just so I can see temperature of the water that I'm going to place that Erlenmeyer flask into. I'm going to take and run this here. And maybe if we want to make a prediction in the chat, and I'm going to add this into my hot water. And what we should see is as I add it into the hot water, we see pressure increasing. It looks like I might have a leak someplace because my pressure increased and then it started going down again. So I might have to chase a leak. But obviously we are limited on time today. I actually wouldn't start this experiment with the water being hot. I would actually start this experiment with the water being room temperature, place the flask in the water, and then allow that water to heat up along with the air in that flask and measure the temperature and pressure together. So yeah, it looks like I've got a leak in here because we saw that pressure go up and now it's dropped down. Not doing exactly what I'm hoping. But if you want a little bit more direction with this last experiment on my STEM kits, we do have a series of lesson plans using the Labdisc on the ideal gas laws. So they deal with all the different relationships between gases. This last one is actually called Boyle's law. So if you want to look that up, you'll find that lesson plan. And we are coming to the end of our time here. So I do want to just share a little bit of other ideas. Obviously, I didn't have time to show everything possible, but some additional things we can look at. Physical science using the Labdisc, doing acid-base titrations, talking about air resonance, measuring circuits using the voltage and current sensors, galvanic cells in chemistry class, looking at saturation of solutions, and using that O2 sensor to measure conductivity or measure that saturation of solution, and doing some experiments on melting point using the temperature sensor and ionic or covalent compounds using a conductivity sensor. And just to sort of open things up to everybody who is not super familiar with everything Boxlight does offer, we do offer much more beyond STEM. I know this is a STEM-focused presentation and talk that we're having today focused on the Labdiscs, but we offer everything that a classroom could possibly need, from flat panels, classroom audio, different intercom and paging and safety systems, as well as other areas of STEM like 3D printers, STEM curriculum as well, and all of the training and support that you need on that. And next week, we're going to be back with Hannah again, who is going to be using the Labdisc Xploris, which is our newest product, to talk about how we can use pixel grids to teach math concepts in K-8. So I encourage you to come back if you are a K-8 teacher. I encourage you to come back and check that out next week with Hannah. And like I said, in a couple weeks following that, I'll be doing another session on how the Labdisc can be used in an environmental class setting for different experiments. And most of the experiments that you saw today, we do have lesson plans available for those on my STEM kits. I believe Hannah, maybe Hannah could post a link in the chat to my STEM kits for me. If you haven't had a chance to check it out, you definitely want to do that because there's tons of lesson plans there for your Labdisc, as well as 3D printing lesson plans too. I will stay on just for a few minutes longer if we have any questions in the chat. Otherwise, thank you everybody for your time today, and we hope to see you next week.